So I'm going to pick B on the left this time, A on the right, and we're going to go the other direction so that you see all possible cases. We're going to use beta here, alpha here. Okay, same problem. MA is given, MB is given, alpha is given, beta is given, and now mu k is given, and mu s is given. And MP is not given. So we're still really dealing with massless pulley. And we're being told that the system is accelerated in the counterclockwise direction. So B is going down, A is going up. And we're still looking for that magnitude of the acceleration. All right. Okay, let's go cranking. Object A. Weight. So far, so good. Nothing new under the tree. Second, normal force. And A, no problem. Third, TA, no problem. Third, oh wait, that was already third. Fourth, now we have friction. We're looking for the acceleration, therefore we know Newton's law. Second will be used, and we know we're moving, therefore we know it's Fk that we have to deal with. Since object A is going up, it's not only Fk, but it's Fk coming down. Therefore, this is mu k, and the n is this n. All right. So far, so good. B. Again, weight. Normal force. Let's call this NB. Tension. TB. And then friction. B is coming down. Therefore, we still deal with Fk, and Fk is opposite direction of motion. Therefore, Fk must be up. So in this case, mu k and B is in the same direction as the tension. Does everybody see the difference? The friction is down for A because A is going up, but the friction is up for B because B is going down. All right. We realize that B and A are connected to one another, so we know we can use Newton's third law. We know that in between there's a stupid annoying pulley, but there is no mass for the pulley, therefore we can consider it massless. Therefore, we can make the assumption that the tensions are the same, and hence TB is equal to TA. And this will allow us to write two equations for A, two equations for B. That's four equations, and be dealing with four unknown: NA, NB, T, and acceleration. If we didn't make that assumption about massless pulley, we'd be screwed. We would have too many unknown. We should go home. Okay? Or we need to find more equation. That's what we will do in chapter 10. But until then, we're stuck with 4. All right. Let's complete our free body diagram. A is going up the inclined plane, therefore in the same direction as my positive T. Therefore, I'm going to pick positive T as my positive X, and positive y along NA. Similarly, object B is going down the inclined plane, therefore opposite to the tension. So I'm going to pick this as my positive X and my positive Y. Same as before, no biggie. Now angles, same again, weights as an angle associated with it. A is about alpha, while B is about beta. A is including alpha either between it and negative y, or it and negative x. Which one is it going to be? Is alpha between your weight and negative y, or your weight and negative x in the A free body diagram? Take a couple of seconds to go through the method we just saw, two-step method, and confirmed that alpha is here between negative y. Thank you, Haruka. So please practice those identification. Very, very important. Similarly, where will be beta? Again, negative y, Honoka, or do you think this time would be positive x? Or anybody else? All right, perfect. You got it. That's it. All the work is done. Now it's just math. It's just chapter 2 and algebra. So, two equations here. Where's my x? Okay, it's there. So t, and then I'm going to go clockwise. So Na is 0. Bear with me, Ray. I'm putting my 0, but if there are no u, ignore them. And then negative mu k Na. And then negative mag sine. And this is MAA. And in the y, my t is 0, Na is full on Na and positive, mu kn is 0, and my weight is going to be negative mag cosine alpha. And this is 0. All right. Similarly, where's my x? Right there. So I'm going to start with the weight and go counterclockwise. So I'm going to have negative, positive, mbg sine beta minus mu k and b and minus t. And then 0 and b because it's entirely in the y direction. And this must be equal to mb because I'm doing object b times a. And in the y, if the top one is sine, then the bottom one is cosine. I don't have to think about it. I just have to check the signs. The cosine adjacent is opposite to my negative positive y, so negative. Those two buggers are 0, and NB is the only one that survives. And the sum of all those guys is 0. Up. That's it. Done. Now I have 4 unknown, 4 equations. T, Na, Nb, and the acceleration. So usually the method being used here is A is in the first and third equation, and they both involve Nb and Na. And those little buggers are all by themselves in the second and fourth. So solve for Na on the second equation, solve for Nb in the second equation, and substitute in the first and the third. And then you combine those two. So let's do that. Where's my pen? Here. So, and then you can add equation 1 and 2 because T has positive here and negative here. So we can do everything in one sweep. Whoops. So T is going to disappear, negative mu k Na, but Na can be solved from equation number 2, which is Ma cosine alpha times G. Then the next term is negative mag sine alpha. Then I'm going to add all the terms on the left-hand side of the third equation, which is positive mbg sine beta. T is going to disappear, and then the only one remaining is mu k nb, and nb can be solved from the fourth equation, which is nothing else but mbg cosine beta. And now I can add everything on the right-hand side. There's only 2 buggers, same as before, MAA plus MBA. Done. And now we can solve for A. Okay, there is something common to all the terms, that's G. And then we have 2 MA and 2 MB, so we can combine a couple of things. So, blah, blah, blah. MA is negative everywhere, so let's start with MB. We're going to have a sine beta minus a mu k cosine alpha. Oh no, cosine beta again. And then negative MA. And then we have sine alpha positive mu k cosine alpha. And I had factored the G out. So here it is, putsch. And I divide by the Tory inertia, MA plus MB. And this is also in meters per second squared. So always look at the signs of your terms. Again, you know that the denominator is always positive for an Atwood system. It should always be the total inertia. Makes sense, because the total mass, as you increase it, will decrease the acceleration. That makes sense. Second, all the terms that has a mu involved gotta be negative, because friction is always, has a purpose in life to always opposite, or to be opposite direction of motion. So sure enough, this gotta be negative, and this got to be negative. Good. Now you know that the weight of B is going to be the one that creates the acceleration. That's the heavy bugger. Should be positive. Positive. Makes sense. And of course, you know that the more you're going to increase the weight of A, then the more you're going to decrease the acceleration. So it should have the opposite function. Hence, you would expect a negative sign. And sure enough, here it is. So always check for your signs. It should always be consistent with the direction of motion that was assumed, and that's usually actually always given to you. The only time where you will not be given the direction of motion is, of course, if the system is at rest. Then you're going to have to figure out the tendency of motion by calculating the net force, as we've done on the first problem. Okay?